Class 12. Today we are going to understand what is Q factor for an LCR circuit. Q factor is a ratio of potential difference across inductance coil divided by the total applied EMF in the circuit. It is taken in the case when resonance is happening. That means omega L is equal to 1 by omega C, which is the case of resonance, and in that case you see omega R, that is resonating angular velocity, is equal to 1 by under root LC, which is the case of resonance, and so Q factor becomes finally 1 by R under root L by C. You see also, even if we also define Q factor, which is same as the ratio of potential drop across capacitance divided by total applied EMF in the case of resonance. So again, if you proceed taking this relation Q factor is equal to VC by E, you will finally come to the same result. Q factor is equal to 1 by R under root L by C when you use the relation omega R is equal to 1 by under root LC. Now in case we have defined Q factor, this is only to indicate what is the sharpness of selection or rejection of a particular frequency. In this case it is LCR series circuit, so series circuit is having largest current when it is in the resonance case, and for that situation the peak of the current will be maximum. As the frequency approaches the resonating frequency, the current approaches to the maximum, and that is shown by the peak. Greater is the Q factor, greater will be the peak, and that is possible when we keep small r value for a given L and C constant. All together you can see the lowest Q factor will have lowest bump, and that is possible by taking a high R value capital resistance, so keeping L and C constant. And Q factor can be overall seen is the inversely proportional to R, directly proportional to under root L, and inversely proportional to under root C. So these three factors will dictate the variation in Q factor. Now students, we proceed to the another facts which we have to study about the reactive circuits. When we take two inductance coil in series, then the total EMF across the coil will be the sum of individual potential drop. The total potential drop across the coil will be the sum of individual potential drops, and therefore we write E is equal to E1 plus E2. Now we also know that potential drop across inductance coil is equal to L di by dt. Using this relation we get L series is equal to L1 plus L2. It is similar to the case of resistances in series. The expression is alike. Now in same fashion, when we take inductance coil in parallel, we have total current drawn is equal to the sum of individual current drawn by the two coils, and also we know that E is equal to L di by dt. Therefore di by dt is equal to E by L for inductance coil, and on putting the value of I and I1 and I2 in the expression, we get again 1 by L parallel, that is equivalent inductance of two inductance coil when placed in parallel is equal to the sum of the reciprocal of the individual inductances, which is again similar to the expression of equivalent resistance when they are placed in parallel to each other in a given circuit. So now, students, we shall be discussing the next topic next day. Thank you and have a nice day.